So far we have talked about mostly autonomous systems, and we studied the stability properties of the origin, which we assume to be an include point of an autonomous system. Okay, and we said the most powerful and most general tool that we have in our disposal to establish stability and asymptotic stability of the origin of an autonomous system is the method of Lyapunov functions, okay, or Lyapunov's theorem, where the theorem stated that if you have a positive definite function called a Lyapunov function, which has a negative definite derivative along the solutions of the system, then the origin of the system is asymptotically stable. Okay. In addition, if the Lyapunov function is radially unbounded, then asymptotic stability is global. Okay. That is, no matter where you start in the state space, you always converge to the origin, okay, the equivalent point. Today we will, for the first time, consider a control system that is not an autonomous system, but a system that has also a control input, which is supposedly in our disposal. That is, we can choose whatever input we like to be applied to the system. And by choosing the proper input, what we want is, we want all the solutions in the system, all the solutions of the system to converge to the origin. Okay. So what we're going to do in this lecture is, given a control system that has to be in some special, that has to have a special structure, we'll see how Lyapunov's theorem can be used to design a feedback law. Okay, so if you close the loop with that feedback law, the closed system becomes autonomous, and that the solutions of that system all converge to the origin. In other words, the origin of the closed system becomes asymptotically stable. Okay, so we're going to study that method under the title backstepping, and in order to be able to apply backstepping, the system has to have a special right-hand side. It's called a system in strict feedback form. And one special case of a system in strict feedback form is the following. Eta dot equals f eta plus g eta times xi, and xi dot equals u. Okay. Suppose that this is our system. Okay. With state eta and xi considered together. Eta is a vector in Rn, and xi is a scalar. Okay, therefore the overall state of the system is, or the overall order of the system is n plus 1. And u here is a scalar signal, which is our control input. Okay, so we can choose however we like for this signal here, u. So let's write them down. What we have is eta is a vector in Rn, xi is a real number scalar, and together they make the state of the system. So the order is n plus 1, and u is what we call the control input. Okay. So clearly, since this is signal, this signal is scalar. Xi is scalar, therefore its derivative is scalar, which equals u. Therefore, u also must belong to real line. It's also a scalar. Okay. Now we make certain assumptions about this system in order to develop the method that we will develop, named backstepping. This is our assumption. Assume that there is a known feedback law denoted by phi. Okay, so this is a mapping from Rn to real line with the property that it's 0 at the origin. This 0 is the 0 vector, and this 0 is a scalar 0 because it's a mapping from Rn to R, under which the origin eta equals 0 of the subsystem eta that equals f eta plus g eta times phi eta is asymptotically stable. Okay. Is asymptotically stable. Okay. So eta is in Rn, therefore this f is a mapping from Rn to Rn. Psi is in R, it multiplies g eta, therefore g eta must be also a vector in Rn. Therefore g is a mapping from Rn to Rn, just like f. Okay. And here we are assuming that there exists a feedback law phi, a function, such that if you replace psi, this scalar, with phi of eta, and consider only the upper half of the system as an autonomous system, eta that equals f eta plus g eta f eta. This is in Rn, this is Rn, this is scalar, therefore everything is on Rn. Therefore eta that equals, let's call f tilde of eta. So we obtain an autonomous system here. We are assuming that the origin of that autonomous system is asymptotically stable. Okay? And that stability is established through this feedback law, which we assume exists. Okay? We either figured it out in some time earlier, or somebody gave it to us. Moreover, okay, so we keep assuming we know the Lyapunov function that's differentiable and positive definite through which we establish the asymptotic stability of the origin. Okay, eta equals 0. V is from Rn to R that satisfies V dot along the solutions of this autonomous subsystem is negative definite. That satisfies that, which is the inner product of the gradient of V with respect to eta and eta dot, or the right hand side, which is plus g eta phi eta. Okay, so this is V dot, and this is less than or equal to minus w eta, and w is some positive definite function of eta, therefore minus w is a negative definite function of eta, with some positive definite w Rn to R. Okay, so once again, what we have in our hand is the following system. It's a nonlinear system with control input. Okay, and it has a special form. Eta that equals some mapping f eta plus some other mapping multiplied by the last state variable, eta, which is scalar. Okay, and eta that equals the control input. Okay, so you apply control input. From here, you integrate it, you obtain eta, and then that eta, in a sense, drives the upper subsystem, okay? Here, eta system. Now, our goal is the following. Find a suitable control input U to stabilize this entire system, okay, which has a state eta and xi considered together. Stabilize the origin of the original system. Eta xi equals 0. So this 0 is a 0 vector in Rn plus 1. Okay. And how are we going to construct this control input or the feedback law is through the information that we're given, which is this phi feedback law, which works for the upper half subsystem. Okay. And also we're going to make use of the Lyapunov function, which also works for the upper half subsystem. Okay, when xi is replaced by this feedback law phi. Okay, so let's therefore begin approaching our goal or begin our solution by rewriting the system in terms of phi, so that it will make us see certain things in a clearer light. Solution. First, rewrite the original system. That is the differential equations describing the system as eta dot equals, not that eta dot equals f eta plus g eta times xi, and eta dot xi dot equals the control input. Now we know that phi eta, if the right hand side for eta system, subsystem, were this, then the origin eta equals 0 is asymptotically stable. Okay, but the right hand side for eta dot is not this. Okay, it's instead f eta plus g eta times xi, the other state variable. So it's a little bit more complicated than this desired form. So therefore, the original right hand side equals g eta xi minus phi eta. Okay. Now that this g phi, and here we have minus g phi, they cancel one another, and what we left with this eta dot equals f eta plus g eta times xi. Okay, so that's the original. That's the original right hand side. But we write this origin. We write that original right hand side in a little bit longish way, because we want to separate two things. Okay, here we have the nice term. If this term didn't exist, then everything would be fine. Eta would converge to 0. But we also have this unwanted term. Okay, so we will try to figure out how we can make this unwanted term converge to origin, converge to 0 as time goes on, so that this eta system converges to this, and eta would go to 0. Okay. But also we also want xi to go to 0, and xi that equals u. Okay. Now, for to see certain things better, let's apply a change of coordinates to the system and introduce a new state variable under change of variables. Okay. Now instead of writing this as an eta xi system, we can write it as an eta z system. Okay. Two representations are equivalent in the sense that we can go from one to the other. So the transformation is valid in both directions. And the new coordinate that we define is this xi minus phi eta. Okay, this is scalar, phi eta is scalar. Therefore, z is our new state variable, which is scalar. Now, what we're going to do is we're going to rewrite this system, the original system, in terms of eta and z instead of eta and xi. We have plus okay, a nice term, times g eta times this difference, which we want to be 0 or converge to 0 eventually, because if this difference converges to 0, then this term disappears and we're left with this nice term and everything converges to 0. So g eta times that, and this thing now we're calling z. It's our new state variable. Okay, z. And then system is n plus first order, therefore we also need z dot to have the complete description of the system. What's z dot? Z dot is xi dot minus phi dot. What's xi dot? Xi dot is u. Okay, so what we have is u minus phi dot. Okay, this is time derivative. And what's phi dot? Phi dot is partial derivative of phi with respect to eta. This is just the gradient of phi with respect to eta. Then you take the transpose. Okay, so this notation is a row vector notation times time derivative of eta. And time derivative of eta is here. Okay. F eta plus g eta times xi. Okay, and then xi can be written as z plus phi of eta, so everything can be represented, can be written in terms of zn, eta, and the input. Okay, so let me squeeze it here. Partial means gradient of phi with respect to eta. This is a column vector by definition, and then you take the transpose, and this is a row vector therefore. Okay. Now let's call this whole thing V. Let's call this term V. Okay. And from now on we're going to treat it as if it's our control input instead of U. Okay. And we can do that because we can figure out V as what V should be as a control input, and then whatever V is, which works, in the very end we can let U equals that verb V plus this term here. Okay? So it's just a simplification in notation. We're calling this term V, and we're going to treat it as our new control input. So what we have, therefore, is the following. Finally, we have the following. Eta dot equals something and z dot equals something. So we start with an eta xi system. Okay, eta is in R and xi is a scalar, and together they make the state of our system. Xi dot equals u, u is our control input, and what the goal is picking a feedback law, figuring out the feedback law, so that when you close loop through that feedback law, the autonomous system, the closed loop system, or the origin of the closed loop system becomes asymptotically stable. Okay, and to our goal, to be able to reach our goal, we use some information that's already given. For instance, we know that we have some feedback law defined over eta, such that if you consider only this system, the origin of this system is asymptotically stable, and we have a Lyapunov function that establishes that asymptotic stability. So in our design, therefore, it could be helpful to use that phi, and that was our goal. Okay, that was our aim. So what we did is we wrote the original system, which was f eta equals f eta plus g eta times xi, in this new form, eta dot equals this good, nice term plus g eta times z. And z is this difference, okay, psi minus the feedback law. And then, instead of letting the second state variable psi, we switch to, after coordinate change, z, and z dot is psi dot minus phi dot. Psi dot is u, and phi dot is that term here, and u minus that term is our right hand side for the z system, okay, or z subsystem. And this chunk we're calling through the shorthand notation v. So what now becomes is f eta plus g eta phi eta plus g eta times scalar z, our new state variable, and z dot is v. Okay. So we want to make z go to 0 in such a way that this term disappears fast enough, in a sense, and eta system becomes eta equals this, more or less. Okay, and then this phi then guarantees that eta goes to 0, and we already, well, we will have established that z goes to 0, therefore eta and z goes to 0, okay? Eta going to 0, that means phi is going to 0, because phi 0 is 0, and z is going to 0, therefore psi must also go to 0. Therefore, eta and psi, which was the state of the original system, goes to 0, and the origin of the original system, therefore, is asymptotically stable. Okay, so, but that requires a rigorous demonstration, and also we haven't yet to choose a proper v. Okay. Now, to design a stabilizing v, okay. Now we're talking about the new coordinates a to z. We want a v that stabilizes the origin of the new coordinates a to z. And by stabilizing the origin a to z equals 0, we will have automatically stabilize the origin eta psi, the origin of the original system. Stabilizing v, and eventually stabilizing u. We can use Lyapunov's theorem. For that, we require a Lyapunov function. And how we're going to construct the Lyapunov function is as follows. Let's use the so-called composite Lyapunov function. Okay. Which is Vc eta psi equals v of eta. This Lyapunov function is Lyapunov function for the eta subsystem, and we know that it works for this autonomous system. Okay, and what we do is we augment that Lyapunov function by adding this positive term, 1/2 z squared. Okay, therefore this whole thing is a Lyapunov function for the eta psi system, because z is psi minus phi, okay, by definition, and therefore this whole thing is in terms of eta and psi. And it's not difficult to see that it's positive definite with respect to eta and psi, because phi of 0 is 0 by assumption. Okay. Now, what we want is, so this is a positive definite function, so it can be used as a Lyapunov function, but to establish asymptotic stability, we have to have a negative, it has to have a negative derivative, okay? Negative definite derivative along the solutions of the system eta z system, okay? And then what we're going to do is we're going to compute that time derivative. We're going to compute z dot, and that will be in terms of V, and we will see by looking at that derivative whether we can choose a V such that that time derivative of Vc dot is negative definite. And if we can do that, then that V would work, and that would make the origin of the system asymptotically stable. And from that V, we can figure out the original control input U, because U is simply V plus this term here. Okay, so therefore what we once again want to do is compute Vc dot and try to see whether we can choose a V that makes that Vc dot negative definite. And then we have asymptotic stability by Lyapunov's theorem. Okay, let's go ahead and compute Vc dot. Then we can write Vc dot equals, okay, Vc dot equals this dot plus this dot, and this dot is gradient of V taken in a product with eta dot, okay, or this row vector, which is the transpose of the gradient of V with respect to eta, times eta dot, and eta dot is here. Okay. F eta plus G eta phi eta, okay, plus G eta Z. So let's write it as a separate term, plus times that G eta times Z. This is a row vector, this is a column vector, Z is a scalar, therefore this whole thing is scalar. This is a row vector, this whole thing is a column vector, therefore this is scalar, so everything is fine. So this, what we have written down is V dot. Okay. We also have this term, which is time derivative of this is gradient of this with respect to Z, which is just Z, and then we multiply with that time derivative of Z, which is Z dot. Okay. In other words, we have Z times Z dot for the time derivative of the second term, and Z dot is what we're calling V. Okay. So we have therefore Z times V, both scalar. Okay, so this we know is less than or equal to minus W of eta. So that we know by assumption. This inner product, or this product of the partial V with respect to eta with this right hand side is what we're calling, or what we're calling W of eta, minus W of eta, and we know that this is a negative definite function by assumption. Plus we have this term here, partial V, partial theta G of theta Z plus ZV. Okay. Now what we want is, we want Vc dot to be negative definite. We already have a nice term here, negative definite in terms of eta. And here we have an indeterminate term. Okay, it could be either positive or negative, therefore it's possibly harmful. We have to, if we can, get rid of it. And here we have V. That's a signal that's in our disposal, so we can choose V however we like. And what we want to do is we want to choose such a V so that this whole thing becomes negative definite with respect to eta and Z. Okay, and one way to do that is choose V, okay, our control input, minus Kz, where K is a positive constant. Okay. If you choose V to equal that, then what happens is ZV, okay, will have minus this term, therefore this term can be cancelled, and moreover we have Z times that term that makes minus K Z squared. Since K is positive, that would be a negative term in terms of Z. And we would have minus W eta minus KZ squared. Okay, so we use V to cancel this potentially harmful term, plus to obtain this negative term in terms of Z. So the whole term, this minus W eta minus KZ squared, is negative definite with respect to eta and Z. And that's what we want. So we're basically done, because by choosing V as such, and thanks to the Lyapunov's theorem, what we establish is we establish that the origin of the system for which this is a Lyapunov function, that is the eta Z system, okay, is asymptotically stable. Therefore, eta and Z converges to 0. Eta converges to 0 means phi converges to 0, and Z converges to 0 means this is 0, this is 0. Xi must also converge to 0. Therefore, the origin of the eta Xi system is also asymptotically stable. And then the last thing to realize is that V was not the original input in our system, okay? So the original input was U, and V and U are related to one another through this relation. This whole thing is V. So for the original control input, what you have to do is you have to add to V here this term. And then everything will be in terms of eta and Xi. That will be your stabilizing feedback law. So let's summarize what we figured out. To summarize, we have constructed composite Lyapunov function, eta, Xi, and eta and Xi, they were the states of the original system. Eta is in Rn, Xi is in R, which is scalar. That we constructed as V eta. This function is by assumption, we have that function by assumption, so it's given, plus 1/2 Z squared, and Z is defined as this difference, Xi minus phi of eta squared. Okay, and BC is positive definite with respect to eta Xi. And then we see that by choosing V as that term, we have minus W less than equal to minus W eta minus K times Z squared. And this here is Z, so we have Xi minus phi eta squared. Okay, and this is also, it's clear that it's negative definite with respect to eta and Xi, okay, because K is a positive number. We see that is negative definite. Okay. Hence, the origin eta Xi by Lyapunov's theorem is asymptotically stable. Provided that you close the loop with that control under the feedback. Okay, V equals that. But the original control input was U, so we have to express in the end everything in terms of U. So U is our feedback law now. That is, it's a function of the state, eta and xi. And that equals, so this was v, that for u is v plus that term. So f eta plus g eta xi plus v. And then what's v? Okay. So we just, this minus u minus this is v, so we just wrote u equals that term plus v. Okay, just we rewrote this equation. And what's v? V is here. Okay, so the very final answer hence is partial by partial eta f eta plus g eta xi plus partial v partial eta g eta minus k z. And what z is this difference? Xi minus phi eta. Okay, it looks a little bit complicated. We have a lot of terms, but it doesn't matter because we have established through a solid Lyapunov function that the origin is asymptotically stable. Okay, so moreover, if all assumptions that we started with hold globally, and if the eta is radially unbounded, so as it grows as the norm of the overall state grows, then the origin eta xi equals 0 is globally asymptotically stable.